Okay, welcome back to the video. All right, now the next thing we look at the shape of complex ions and coordination number. Now, what is that shape of complex ion? It's same like what we learned in molecular shapes. Okay, it depends on how many bonding pairs and how they arrange in space. So you get the different shapes. Now, it's very lucky we only have these shapes in these slides that we're going to learn. All right, and one more good news is we only need to focus on octahedral, all right, and square planar. These are the common molecular shapes for transition metal complex. Okay, so let's go through it again. So shape linear means you have 2 bonding pairs. Square planar can be 4 bonding pairs, or tetrahedral, also 4 bonding pairs. Octahedral is 6 bonding pairs. Now, what is that bonding pairs here? The bonding pair is referring to the dative covalent bonds. And how many dative covalent bond is actually based on the number of ligands and the type of ligand. All right, let's put it aside the bidentate and polydentate. We focus on monodentate. All right, let's assume that the ligand here are monodentate. So you're going to form 1 dative bond each. There you go, you have 2 dative bonds. So this one will give you a linear shape. All right, square planar and tetrahedral, both with 4 ligands and 4 dative bonds. Octahedral, 6 ligands with 6 dative bonds. Okay, so this is how they arrange in shape. And what about coordination number here? Coordination number, or here, this is actually indicating the number of dative bonds. All right, if you have 3 dative bonds in a complex ion, then the coordination number is 3. If you have 6, then it's 6. If you have 4, then it's 4. All right, so remember this, coordination numbers equivalent to the number of dative bonds. It's not the number of ligands, because the ligand can be bidentate or polydentate, which means I can have 1 ligand but forming 6 dative bonds. So the coordination number is still 6. Okay, again, if I have 3 ligands and all 3 are bidentate, so how many dative bonds would I get? So bidentate means 1 ligand forming 2 dative bonds. I have 3 bidentate ligands, means 3 times 2, 6. So again, the coordination number is still 6, even though the number of ligand is just 3. Okay, I repeat again, the coordination number is equivalent to the number of dative bonds in a complex ion. All right, so that's complex ions and coordination number. Now, basically, we have done with the introductions of all the transition metal complexes. Now, what is transition metal complexes, how to name it, and what is the shape, and what is the coordination number. Next, we go into the main point where we should explain why transition metal complexes form colored compound. Okay. Now, the keywords here, how they actually form colored compound is actually DD splitting. All right, what is that DD splitting? DD splitting is the split of the d orbitals. Now, from what we learned, d orbitals, how many orbitals we have in the d orbitals? We have 5. All right, 5 different orientations. Okay, we're going to learn the symbol later. So we have 5 different orientations for the d orbitals, and each orientations will have 2 electrons. So total, we can put in 10 electrons. All right, and these 5 orbitals will tend to split under the influence of the ligand. Okay, when they split, some process going on, and that's how you get colored. All right, now these are the words that explain the whole thing. So I'm going to draw out the diagram so it's easier for you to explain. Of course, you can read through the slide later. Okay, now let's see. I have, let's say, again, I love copper. So copper 2+, the configuration is argon 4s1 3d10. Oh, sorry, that's for copper. So 2+ is without 4s. All right, so no more 4s. And 3d left 9 electrons. Okay, 3D left 9 electrons. So this is the configurations for copper 2 plus. All right, now assuming that I'm drawing the 3D orbitals here, I have 5 3D orbitals. Okay, so this is the d orbitals and we put in electrons. You have 9, so 1 through 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 electrons here, 1 empty space. All right, now what happened is when these copper 2 plus actually expose to 6 water ligands, for example. Okay, now each ligands we're going to donate 1 pair of electrons to the copper 2 plus, and the shape or the structure will be like that. I redraw it again. This is copper 2 plus, and then the water molecules will form dative bonds with it. I have 6, so the molecular shape will be H2O, H2O, H2O. Now I put O first because O is the one that donated electrons. You can see every single bond is actually bonded to O. So this is the overall shape, and this is octahedral. All right. Now this is how they form. Now when each water molecule actually donate a pair of electrons to copper 2 plus, what will happen? Now copper itself has 9 electrons. Okay, copper itself has 9 electrons. So what will happen? When all these water donate the lone pair, it will start repelling with the 9 electrons because electron that tends to repel. All right, so the valence 9 electrons will get repelled, and this repulsion force will actually split the d orbitals into 2 energy levels. How they split? They split in such a way that 2 orbitals on top, 3 orbitals below. Later I explain why is it 2, 3, why not 4, 1, why not 1, 4. Okay, that's the reason for it. But before that, let's go to the basic. Now, if it's split into 2, right? It will split into 2 and then the electrons will be like that. Okay, and what happened? Here you have an energy gap. Okay, you have an energy gap here. Now what happened when the ligand approached the copper and it split the d orbitals? When these complex ion exposed to white light, okay, white lights exposed to white light, what happened? White light, you have 7 colors. All right, so different colors will have different frequency or wavelength. And different frequency wavelength, you have different energy. Now, if one of the color here match with the energy difference, the energy gap here, then they will start to absorb. Let's say the 7 colors, they only absorb the orange, because the orange color having the same energy value as the energy gap. So what will happen when they absorb orange color? They will absorb the orange color energy and try to promote the lower energy electrons up to the space here, to the higher energy orbitals. So there is a promotion of electrons. Okay, again, so out of the 7 colors from the white light, they absorb orange because the energy level of orange same as the energy gap here. So when they start absorbing, they will promote the lower energy electrons down here, promoted up to the higher energy orbitals. Okay, that's promotion of electrons. All right, what about the other 6 colors that not been absorbed? The rest of the colors will be reflected. Okay, the rest of the color will be reflected. So these 6 colors will get reflected. And when it reflects means we can see the color. So the 6 colors combine and get reflected, we see it as a blue color. Okay, because 7 colors combined, you get white. But if you have out of 7, you only have 6. The 6 color combined will give you a certain color. In this case, if you remove the orange from the 7 colors, you only have 6. The remaining 6 will give you orange color. Blue color. Okay, so that's why copper in water, they observe as blue solutions. All right, hopefully it's good. All right, let's look at the diagram again. Okay, so this is the diagram showing all 5 d orbitals. Now it's time to go through the symbol. We have dxy, we have dyz, we have dxz, and then we have dx square y square dz square. We have seen it in chapter 2, electronic configurations and the orbital shapes. All right. Now let's look at this before we look at lower and higher energy. All right. So these are the arrangement of the orbitals. This is how they arrange. Dxy means the orbital arranged between x and y. It happened to orient it at between x and y. That's why they call it as dxy. And the orbital here happened to be between y and z. So dxz, all right? And here is between x and z. So based on the orientation, they name them. This is a symbol. And dx square y square means the orbital actually lying on the x and the y axis, lying on it, okay, on the axis, not in between, but on the axis. So this is dx square y square. And last one, dz square means the orbital actually lying on the z axis, on it, not between. All right, so you have 5 different orbitals. And according to what I explained just now, it tends to split into 2 energy levels. All right, the one on top, the one with the higher energy level is actually here, higher energy level, which is dz square y square, dx square y square, and dz square. The lower energy is dxy, dyz, and dxz. All right. Now, why these two, the dx square y square and dz square having higher energy, it splits up, and why these 3, 1, 2, 3, having lower energy levels. Now, look at the diagram again. Let's erase the notation. All right, look at the diagram again. Sorry. Okay. Now, this little green ball here actually indicates the ligand or the lone pair of electrons. Okay, from the ligands. And how many ligands we have? 1, 2, 3, 4, 5, 6. We have 6 ligands here. And this is where the directions, they came in these directions as an octahedral. Now imagine, I have electrons in the orbital, and these are the direction, these are the lone pair from the ligands. Will the electrons in the orbital repel with the electrons from the ligand? The answer is no. See that? The electrons in the orbital is actually exist between the 2 ligands. So there will have no head-on repulsion between the electrons in the orbitals and the ligand. Okay, same goes to this. Look at that. The ligand is here, the electrons, the lone pair, and the orbital with the electron is here. So it just happened to be in between them. So there is no repulsion here. Same goes to this, no repulsions. Okay, this tree has no repulsions with the lone pair from the ligand, which means this tree will experience lower repulsion or no repulsions. Therefore, they have lower energy levels. Okay, if you look at high energy level here, dx square y square and dz square, look at that. The ligands coming in from here, and it just direct head on with the orbitals because it's lying on the axis. All right, so the electrons from the orbitals will have repulsions with the lone pair from the ligand. Same goes to this, same goes to this, same goes to this. So when they have head-on repulsions with all the electrons here, what happened? They get repelled, and therefore they have higher energy level because of repulsions. And here, look at dz square. Again, they're lying on the z-axis, and there you go, electrons from the ligand coming in from here and here. So the electron from these orbitals will have head-on repulsions with the ligand. Therefore, these 2 orbitals are going to be at higher energy level due to repulsion. And that's explain why the d orbital supposed to be that. Okay, split into two level, two on top, three below. And now, would you able to name them? The two here is actually dx square y square, dz square. All right, and the three with lower energy is actually dxy, dyz, and dxz. All right, now this splitting only meant for octahedral. If they arrange in different shapes, the splitting will be different because the ligand coming in different directions. This is for octahedral. What if for square planar, they only come up with these four? These two don't have. We don't have these two. Okay, we only have four. So the splitting will be different. But good news is we just need to focus on octahedrals, not other shapes in terms of DD splitting. And that is how they split into two, and that is how they observe colored. All right, now last slide. This slide actually indicates the strength, okay, of the ligands. Now different ligands will have different strength. All right, different ligand, different strengths. Now let's say a d orbital split, again due to the presence of ligand. Okay, it's split into two. In the octahedral shape, you have this and you have this. And how do we know the energy gap here? How do we know the gap is either big gap or a small gap? So how do we know whether it's big gap or small gap? It depends on the strength of the ligands. Now, from here we can see weaker field is here. Iodide is the weakest ligand, and stronger field, carbonyl, is the strongest ligand. This is the strongest ligand, and that's the weakest ligands. Okay, now what is the purpose of learning these strong and weak ligands? Now, imagine that if I have a strong ligand like carbonyl, cyanol, okay, what will happen to the gap? The gap will be big. When the gap is big, see, larger field, larger gap, and it will absorb what color? They will absorb a shorter wavelength color. So, examples of shorter wavelength color. What is the examples of shorter wavelength color? Violet, blue, right? Because these are those with high energy. Okay, now what if we have a weaker ligands compared to carbon? Let's say I have chloro, all right, weaker field, and you will give you a smaller gap, all right. If you have a smaller gap here, they will absorb a longer wavelength light. Examples of longer wavelength light is like red, yellow, orange. Okay, so this is how they absorb light based on the ligand. Okay, so which means different ligands will give you different color, even though the metal ion is the same. Example, copper, we all know that copper will always form blue solutions because when copper dissolves in water, you get blue. What is the ligand in this case? Water molecules. All right, water molecules are ligands. Now, what if I try to dissolve copper instead of water? I try to put copper into ammonia solution, which is ammonia or amine as a ligand. What will happen to the solutions? The solution will change from blue to dark blue. Okay, why there is a change of color? Because different ligand, different splitting, different gap. Okay, different gap, different absorptions of wavelength, resulting in different color. Okay, so we need to know the strength of the ligands so that we can estimate what wavelength, shorter or longer wavelength, will be absorbed and what color will be observed. Now, how do we know? Let's say they observe purple or violet. What is the color being observed? They absorb purple and violet. So what color being observed? We have to look at this so-called big color view. All right. Like just now I mentioned about copper. Copper observed as blue. So what color is being absorbed? The opposite, which is orange. Okay, the complementary color here. So If the solution observed as red, so what is the color of light that being absorbed here for the splitting? Green. Okay, violet, what color being absorbed? Yellow. Okay, of course, we don't have to memorize this because this is given in the data booklet. Okay, it's not in the form of color view, in the form of table. So you can refer to data booklet. Roughly, you will know if the solution appear as orange, which means the absorption is blue. If they observe as blue-violet, then the absorption is yellow-orange. There always has a complementary color here. Okay, that's about it. This is how complex ion show colored in a solution form with different ligands. Okay.